Hey there, I'm srcmake and welcome to the video on segment trees. In this video, we're going to look at the algorithm behind how segment trees work, and we're going to look at the intuition behind how the tree structure works. And I'm actually going to draw it out in Microsoft Paint so you're going to see the recursion. It's going to make total sense to you. And we're also going to look at some pseudocode for how you would actually implement the recursion. It's some actual working C++ code that I wrote so that you can actually see how you would actually implement a segment tree yourself in actual code. So in this video, I'm going to explain what segment trees are. And spoiler alert, segment trees are a tree data structure that are used to represent arrays, and they solve a particular type of problem. We'll go through that in a second. We'll look at the actual problem that they solve. And in this case, it's going to be repeatedly finding the minimum from a range. You can do other things with segment trees, but this video is going to be about minimums. And I'm going to try to go through it kind of quickly because it would take a lot of time to explain. We're going to look at the naive algorithm for how you would actually try to solve this yourself, but then realize that it's a little bit slow. And it's slow because you're not using a segment tree. Now, segment trees are an advanced type data structure that are used in algorithm competitions, and kind of like, if you understand segment trees, you're going to understand merge sort and like a bunch of other algorithms. So it's really important to understand. And if you understand the recursion behind it, it's going to make life like a lot easier, because this is like the use case of trees and recursion and everything else like that. So we're going to look at how you would construct a segment tree by seeing how they're implemented, like how they're actually represented with an actual it's actually an array. We're going to look at how you would fill the segment tree with the actual values that we care about for finding the minimum easily. We're going to look at how you would query the segment tree to actually find the minimum or the value that you care about once you construct it. And then as a bonus, we're going to look at how you would actually update a value in the segment tree after initially creating it. And then we're going to look at the actual C++ implementation that I wrote for segment trees. I wrote it on GitHub. You can find it right here. There will be links below the video. But we're going to actually see running segment tree code, which is going to be really cool because it's really nice. I haven't seen a lot of other good intuitive code written of segment trees besides Geek for Geeks. So this is going to be nice. And then we're going to see how we can extend a minimum segment tree to other problems like maximum and sum and returning index and a bunch of other things like that. And it's all going to make sense. So all of these resources, everything except for the pictures, because I'm going to do the pictures right here in this video. So you want to stick around. All of this is right here on my blog, my website. There will be a link to this page below this video. Below this, you can click get to this page, bookmark it so you can save the code for later. That would be a good idea. And while you're down there, hit the subscribe button and the like button for this YouTube video and channel. So thanks. Let's actually go into this now because this is going to take a bit of time. So segment trees are a tree data structure that are used to represent arrays. So for example, if you had an array like this, you might want to represent it as a tree to query things a little bit more easily. It's an advanced data structure that you're using. And it's helpful for certain things like finding ranges in an array. So for example, if we had this array and we wanted to find the minimum from index L to R, that's when you would try to use a segment tree, because it's good for ranges within an array. That's the use case for it. So for example, if we had an array like this and we wanted to repeatedly find the minimum from a range. So for example, what's the minimum from index 0 to index 6? Well, if we look at this look through it, you can see that 1 is the minimum pretty easily. But what about from index 0 to 5? Well, if you go through these numbers, it looks like 2 is the minimum. 2 is the minimum. What about from index 1 to 1? Well, in that case, we only have one possible choice, and that's an 8. But what about from index 4 to 5, 9 and 4, the minimum there is just 4, and that's easy to see. That's really easy for us to see as humans for this simple array. But what if we had to program this and write this, in a program? Write code for this. Well, the naive thing that we would try to do is probably just use a for loop. And we'd probably use some algorithm like initialize a minimum to be some really big number, like 1,000,000, and then go through the range that we care about from L to R. And then at each index from L to R, we would say, oh, if this number is smaller than the minimum that we've seen before, we would update our minimum to be this new value. So for example, if we were going through this original array and we were trying to find the minimum from 1 to 4, we could say, oh, let's start out and say that the minimum is going to be 1,000,000 because that's like super high. Then we look at the first element, index 1, and we say, oh, 8 is smaller than 1,000,000, so 8's our new minimum. We look at the next value, 5 is smaller than 8, so 5 is going to be our new minimum. Next index, 3 is smaller than 5 now, so 3 is going to be the actual minimum that we've seen so far. Then we look at the last value, 4, and we say 9 is not smaller than 3, so we want to keep 3 as the minimum value. And then after going through each one of those indices, we can say, oh, 3 was the minimum that we saw, so let's return 3 as the minimum. And that's good. That's actually really simple. But that running time is order n because we potentially have to go through the array, through every element of the array. And that's okay, but if we have to repeatedly search this array, like, do queries multiple times, then that's kind of slow. Order n isn't acceptable. We would like to reduce it to order log n, which is exactly what you think of when you think of trees. Log n means binary or trees. So a segment tree is good if you're asked to make multiple queries on subranges in an array. If you have to make multiple queries, you want to build out the segment tree because it's going to be useful for you later on. If you just have to make one query, just stick with your simple for loop. But multiple queries, segment tree, right? Okay, good. So how would you actually build a segment tree? Well, the first thing I want to tell you is that a segment tree is represented as an array. It's a heap data structure. And a heap data structure just means that if you look at a node in a tree, you can easily find its 2 children in the array by doing some simple calculation. In this case, the calculation is going to be, the left child is going to be 2 times the node index, and the right child is going to be 2 times the node index plus 1. So for example, well, I'm not going to go through the example right now. We'll actually just go through our normal example with the picture, and you'll see how that works. So yeah, let's get into it. So we're going to build out the segment tree for this right here. So let's minimize this and let's go through it. We'll go through the steps together, but our original array is going to be, let's see, let's draw this out really quickly. So the original array is 4, 5, 1, and it looks something like this: 4, 5, 1, and the indices are 0, 1, and 2. And I'm going to go through this kind of fast. You can read through the code yourself a little bit later because I think it'll actually make more sense to you to read through the actual code to see what's going on and how you would implement it. I just want to go through the intuition in this video, and the intuition is going to unblock everything else, which is good. So we want to turn this into an actual array to represent the segment tree. So let's go to our section right here with our pseudocode. And the first thing we need to do, you can see it great, we need to calculate st height. And basically, the original array length, which in this case is 3, we have 3 elements. We're going to do the log2 of it, and then we're going to do the ceil of it. So I've got Google open right here. And let's say equals log, let's make this a little bit smaller. So you can see, yeah, you can see, equals log2 of 3, and that value is 1.5. We want to do the ceil of that. So the ceil of 1.5, we round up to make that 2. And so we say st height is going to equal 2. The next calculation we need to do is 2 raised to st height. So 2 raised to 2 is 2 squared, which is 4. 4 times 2 is 8, and 8 minus 1 is 7. So the number of leaves we can expect in our segment tree, the maximum number of leaves is going to be 7. So let's actually create an array of size 7. That's basically what that means. So let's draw that out really quickly. Ooh, this is going to be a tight fit. So 1, 2, 3, 4, 5. Ooh, let's make this. Yeah. Let's do something like this. Okay, great. So, ooh, this looks a little weird, but you guys can deal with it. So this is basically what our segment tree is represented as an array. And we'll say that the indices of this segment tree array are 0 to 6 because we calculated 7 leaves, right? 7 leaves means 0 to 6. It looks a little weird like this, right? We were expecting a tree data structure, but remember, it's represented as an array, but we think of it as a tree. So if we draw this out, let's say this is node 0, and it's got 2 children. It's a binary tree if I didn't mention that before. Let's draw this like this, and this like this, and this like this, and okay, great. So this looks a little bit more like what we're expecting, right? This is node 0, this is node 1, this is node 2, This is node 3 right here. This is node 4. This is node 5, and this is node 6. So notice the colorings right here. You see that this 0 represents this right here in the tree. This 6 over here represents this right here. So we think of it like a tree even though it's an array. Right? Good. It's just an array that represents this, but we think of it like this. It's not too hard. So the next step is filling this segment tree with values. Now let's go over these 3 simple rules. Each node in our segment tree represents a range in the original array. Remember, we're building this segment tree to represent ranges. Each node whose range represents multiple elements would have 2 children. So for example, 0, 0 is a range that has probably no children because it represents only one range in the original array, but something like 0, 2 would represent 3 elements, so it would have children. And so what that means is our root is going to represent the entire original range. In this case, it's 0, 2. And the other important thing that we want to think about is in these trees, we want to split the work in half. That's how we get to log n. So our original range for this node is 0, 2, but that's too much for this one node. We want to break it down. So we say that the left child is going to represent half the range, and the right child is going to represent the other half of the range. So in this case, we have a really small original array. If we broke it in half, we could see that this would be the actual left child and this would be the right child. So we just say, okay, we want to break this down so that this left child represents this range and this right child represents the other range. It looks a little weird because we have a small array, but in bigger, arrays, this would be like a lot of time saved because the height of our tree would be short compared to the range of the original array. So this 2, 2 actually is good enough. We can cross out these 2 children. We're not actually going to use them because 2, 2 represents just one range in the original array. This 2, 2 represents just this right here. But this 0, 1 is also too big. So we have to come and we have to break this down a little further. In this case, if we break this down into half, we get 0, 0, and we get 1, 1. And so the thing to keep in mind is that our segment tree represents ranges, and at each node, we want to break each range down in half. For our root node, it actually just represents the entire original array, the entire range, which in this case is 0 to 2, right? That's good. So think about it like that, but we actually need to fill this in. So the first thing that we need to do in this code, and we start out with fill st, and we recursively fill the minimum from that. We start out with the root node, which represents node 0 from, you can't see that well. We represent node 0, right here, this green, from range 0 to 2. So we're saying node 0 represents 0 to 2. Original array length is 3, minus 1 is index 2. Right? Great. So what we want to do is let's look at the pseudocode. If the range is only one element long, it only has one possible choice for the minimum, fill the node in. That if statement will apply to the leaf nodes down here because they only represent one element. But if you're not a leaf node, what do you have to do? You have to say, oh, well, you know what? I've got children. Let me look at these 2 children of mine, and I'll pick the minimum between those 2. So we look at the root node, and we do some calculations to find what the minimum from the children are, and we recursively do that. So we start out with this root node, and we say, I don't know what my minimum is because I don't, represent just one element. So I'm going to have to ask my 2 children. So it asks node 1, its left child, and says, hey, what's your minimum? Node 1's like, I don't know my minimum. I'm also a big node. So I'm going to have to ask my 2 children. So node 1 comes over here and it says, it has this left child of it. And it says, hey, what's your minimum? This child says, you know what? I only represent range 0 to 0. So actually, I can just look right here and see what my minimum is. So its only choice for the minimum is going to be 4, right? So we update this value right here and it says, hey, I'm a 4. And we update the original array. What is it? This represents node 3. So the segment tree array is going to fill in a 4 right here. So then it's like, okay, cool. Node 1 says, cool, you're a 4. What about you, my right child? What's your minimum? This child is going to be like, you know what? I also only represent one element. So I can just look it up. So node 4 is going to be like, well, index 1 is a 5, so that's what my minimum is. And that corresponds to right here. So this is node 4. We come back to the original array, and that value is a 5. So now node 1 is like, okay, you know what? Okay, cool. So my left child is a 4, my right child is a 5. I want the minimum between those two. That value is going to be a 4. So then we see node 1 is going to update its value to be 4. So then node 0 is like, okay, cool. So my left child's minimum value is a 4. So I'm going to have to ask my right child so I know what to do. Node 2 is going to be like, oh, well, I only represent just this one element. So I'm going to say it's got to be 1. My minimum is 1. So it tells that to node 0. Node 0 is like, okay, so my two children are 4 and 1. Oh, by the way, node 2 is going to update the original ST array. And node 0 is going to know that between its two children, the minimum is going to be 1. That's basically what this code does. That's how recursion works. So we go all the way down. We see that it only represents one element. Then we kind of make our way back up. And we do it in the same order that we just did. That's recursion. So that's it. We actually filled up our segment tree array perfectly. If we look at the original picture that I have over here, it corresponds exactly, well, you can't see that well. It corresponds exactly to this. And that's how you would fill that up. The next thing to do would actually be to query this segment tree for the minimum, because that's why we built it, right? We built this to actually find the minimum in log n time. So to query the segment tree, we also have to use recursion, of course. And there's nothing special here. We start out and we say the minimum is going to be if we recursively start for index L to index R for the root node. Node 0 from its range is going to be 0 to 2, and we just pass L and R to it. So let's scroll up a little tiny bit so you can see this. And what we do is starting at the root, we say, okay, if this node's range is anywhere outside of L to R, then we don't use this value because it would be something weird. Like it would be, we'll see. Actually, you know what? Let's go through the example right now. So let's say that we want to find, not this color, let's do orange. Let's say that we want to find range 1 to 1. What's the minimum from 1 to 1? Well, in this case, we would have to look in our segment tree and we'd start at the root and we'd say, so node 0 represents range 0 to range 2, but this is too big, right? This range is too big. It represents node 2, and node 2 clearly has something that we shouldn't consider for range 1, 1 because it has this 1, and that's going to skew the results. So what we do is we disregard this range right here. And we look at this and we basically just return a really big number because we will look at the two children and we say, oh, node 2 is not in the range. So what we want to do is we want to just return like infinity or something over here and not consider this one. But then we would look at its left child and say, oh, well, 0 and 1 is also sort of in the range, but we have to look at the two children to see, to narrow it down a little bit more. So we look at node 0 and we'd be like, oh, this is also outside of the range 1, 1. So we don't want to consider this value. So let's return a 0 from node 3. And then we would finally look at node 4 and be like, oh, 1, 1 is actually exactly what we're looking for. In this case, it happens to be a single element, but it could be something else. It could represent, multiple elements. In this case, we're just going to return the value. So 5 is valid. We return 5 up here. The minimum between infinity and 5 is going to be 5. And so we return that back up here. And the minimum between 5 and infinity for node 0 is going to be 5. And so we return 5 like that. So basically, what we should consider here, and I'm going through this a little quickly, but we recursively go through the children. And if we ever find a range that's outside of the range we're querying for, like in this case, 2, 2 is outside of the range 1, 1. Even if this was range 0, 1, 2, 2 would still be outside, considered an outsider. So we want to return infinity there, and then just when we return back up, that range isn't going to be considered. And we would look at the other children. In this case, the other thing to keep in mind that I didn't mention is if we were to do like 0, 1, and that was the range, we wouldn't actually need to look at the two children because 0, 1 is completely encapsulated in the range. So we could just actually look at this value itself from the segment tree. We could just say, oh, 0, 1 is represented very perfectly here. I don't actually need to go down to look at my children. I can just know that value itself. And in this tiny example, it doesn't look like it makes a big deal. But in large trees, you don't want to have to go down if you don't need to. It's pointless to look at children. So that's basically what this if statement right here is. If the node is completely within LR, then return this value as the minimum. No need to continue to look down at the children. Good? So disregard anything that's outside of the range. If it's completely within the range, just return its value from the segment tree. Don't even need to look at the children. Yeah, that's basically it. So that's how you would query the segment tree. That's the pseudocode. You can read through it yourself so that it makes more sense if you need to. Let's just get rid of this. And the next thing that we care about is actually updating the value. So let's say that in our original array, let's use a different color. Let's use this blue right here. Let's say that we got rid of this 5 and this value became 3 for some reason. Well, now we have to update our segment tree, right? We don't actually need to build a new segment tree. What we need to do is, starting at the root like usual, and the pseudocode might explain this, but we don't need to go through that. Starting at the root, actually, let's look through this really quickly. Basically, what we pass in is the new value, which in this case is 3, and the index of that, which in this case is 1. So element 1 of the original array got updated to 3. And we're passing that in, and we're starting at the root as usual. Basically, what we need to do is we say, if the start index is equal to the end index, then the node represents just one element. Like in this case, well, we'll look at that. But otherwise, we have to just recursively look at the left and the right tree to see if it matters. So for example, starting at the root, we know index 1 got updated. Which subtree should we update? Well, this node 0 actually has index 1 in it, so it's potentially going to get updated, right? This new value could be better than the other one. So what we need to do is we need to say, okay, 2, my right child, does not represent this index. This index, index 1, is from my left child. My left child is the one that's covering this index. So we need to go to the left child and see if we need to update anything there. So then we come here and we say, okay, 0, 1, my left child 0, 0 does not actually represent 1. Index 1 is represented from my right child. So then we're going to go down here. And then we're going to look and say, oh, I'm 1, 1. I'm the actual element that got updated. I have no choice. I need to update my value. I can no longer be 5. I have to be 3 because my value got updated in the original array. So let me draw that a little better, actually. So this becomes a 3 right here. So we come back up the stack, and now we're at node 1 representing 0, 1. And node 1's like, well, one of my values got updated, right? I might potentially need to be updated too. So node 1 is going to look at its 2 children again, and it's going to say, oh, so my left child is 4 and my right child is 3. What's my minimum? Well, my minimum actually updated. It's actually now 3, so it updates its minimum to be a 3. And now we recursively come back up, and node 0 is going to be like, oh, okay, so one of my children might have gotten updated as a result of this new update. I might need to update my own minimum that I'm representing. So node 0 is going to look at its 2 children. In this case now it's 3 and 1. And it's going to be like, oh, well, 1 is the minimum. That's the same as before. I don't need to do any update myself. And that's basically what you do. So for updates, you start at the root, and you only look at the trees that you need to. In this case, the left tree is the one that was representing the index that got updated. Index 1 was the one that got updated, so you had to look at the left tree. Then for this node, you have to go to its right tree because that had the index 1 that was being updated. You have to look at the index, and you only go to the subtrees that you need to. And then once you do that update, if it actually gets updated at all, well, it technically does get updated. But then once you go back up the tree, you must recalculate what the new minimum is, if there's any new minimum at all. It's possible that nothing gets updated at all, except for this bottom level one that is forced to update because the original array updated. But you still do that check to see, oh, well, let me recalculate my minimum based on my 2 children. And you don't have to recursively go down to do that. If you look at the pseudocode, you can just directly look at the segment tree array for your 2 children because it knows what its 2 children is. So for example, index 1 knows that its 2 children is going to be 2n plus 1. So 2 times 1 is 1. 2 times 1 is 2. 2 plus 1. Oh, no. Okay, left child is 2 times itself. So 2 times 1 is 2. It knows that its element, whatever. I'm actually not going to do this because it's crazy. Is it crazy? No, it's not. But just take my word for it that you can just look up the value itself in here. Sorry, I'm drawing a little bit of a blank, and I know that this works. Moving on, so that's updating. Could you add or delete a value in the original array? Like, let's say that we wanted to update this because we just added I don't know, a 9 in here for some reason. The answer is no, it's actually really hard. You can't update this. What you would have to do is you would have to delete this entire segment tree and recreate a new one. That's basically it. So delete the old tree, build a new one. And that's basically it for the intuition. That's the recursion. That's how segment trees work. It's just a data structure that's represented as an array, a heap array, and each node in the array represents 2 children. Well, it represents ranges, and its 2 children breaks down its ranges itself. So I just want to quickly go through the class. Let's open this back up. Let's scroll back down. So let's go through the code that I wrote that is available on GitHub. I've got the pseudocode right here. This is the simple project under the MIT license. Don't sue me if anything goes wrong. We've only got 2 files in the source folder, and we've got a make file because my name is srcmake, and this is some C++ code. Main.cpp basically instantiates the segment tree that we have with the initial array. In this case, we have a vector. I wanted to do a vector since it was easier. And then you've got a few operations you can do, like print, or you can do query, or you can do update, which I don't see. Oh, right here, update. That's kind of small for you to see. But you can query and you can update, and this is basically how you call segment tree. So you just instantiate it once you build it with the constructor. Let's actually go through the code really quickly. So it's just a simple class, C++ class. You've got the function definitions here, a pointer to the root of the segment tree, because remember the segment tree itself is a root and we want to just access it with a pointer. We've got the lengths that we were using, allocation, deallocation of the segment tree array, filling it in, a few recursive functions, and then the public functions that we need, like updating and querying, that are user facing. Because some of this is like business logic that the segment tree cares about, but the caller doesn't care about. And some of it is like the user is just going to want to call update and say, hey, update my value with this new index, whatever, with this new value. Or query from L to R, right? So we've got a constructor that is going to build a segment tree. This is some beautiful C++ code, by the way. I really recommend storing this repository and saving it for later or reading through it. So we've got the constructor. We've got a destructure, which just deletes the segment tree in case you need to build a new one or something. We've got the querying, which is basically like the pseudocode, but it's written a little more verbose for the C++. We've got updating. And we've got just printing, because printing is useful for debugging. Actually, you know what? Let's do this really quickly. Let's go back. Let's clone this repository just so that I run it for you. And you can see how it works. So let's git clone the repository name. And if you read through this, the README goes through the file structure. It tells you that it's a make file, and all you have to do is write the word make. So let's cd into this. cd segment tree is the name of the folder, and all you have to do is make, and boom, it actually represents what we have in here. So our example from before, this segment tree, I actually use right here. So this is what the tree would look like if you were to build out the tree for this. You could see that there are actually some unused leaves, which is what we expect. Minimum from 0 to 6 is 1, 0 to 5 is 2, 1 to 1 is 8, 4 to 5 is 4. And I have another example in there, but it works. And if it doesn't work, let me know in the comments, because I don't know. There might be a mistake in there, and this just happened to work by chance. But yeah, that's the C++ code that I recommend you read through. The last section before we finalize this is extending the segment tree for other problems. So in this tutorial, we used a range minimum query. We did a minimum segment tree, but it's possible to also do a maximum segment tree. So we could do a maximum, find the maximum of a range instead of doing the minimum. We just want to find a maximum. In that case, if you look at the code, let's just do this code right here. Let's do min. Oh no, let's do min like this. So at each step, instead of just calculating, we said that the minimum for each node was going to be the minimum between its 2 children. Just change this to a maximum. And you could update a few other things, and yeah, just a few lines need to be changed to make this from min to max. So that's super simple. The other thing we could do is find the sum of a range. So for example, instead of saying what the minimum from 0 to 1 would be, which in this case would be 2, we would say what's the sum of it, and in that case it would be 2 plus 8, which is 10. You could also do that with segment trees. That's a really good use for repeatedly querying a range. That's what segment trees are good for, not just max and min. We could return the index of the minimum and maximum value instead of the value itself. So for example, in this segment tree example, we had, instead of doing like, what's the minimum of this array, and we would say the value is 1, we could just say, oh, the index of the minimum is 2, because the value is 1, but we care about the index itself. Maybe that's what we care about in an example. That's perfectly valid. And finally, we can store objects in the segment tree, not just numbers. So our example here was 451, and we broke that out into numbers here. But maybe these are like structs or objects or some complicated things like JSON that, a more complicated structure that aren't just numbers. We could also do that very easily. So that's basically it for segment trees. Segment trees are a data structure that comes up in algorithm competitions and sometimes job interviews. And there's usually no time to code one from scratch. So you should bookmark this page. You should subscribe to this YouTube video, or you should star the GitHub repository so that you could come back and customize it yourself when you need it. Trust me, you don't want to be building all this code in the actual competition. You just don't have time. Keep in mind that this tutorial was meant for demonstration purposes, so there are optimizations and edge cases that we could have covered, even in this code that I wrote right here, that I didn't cover. So you should really go through this code yourself if you really care and see how it works and try to optimize things. Like for example, a lot of my code has this node left child index, node, calculating the indexes. You could abstract this into a function, and this middle index also too. You could move that out into a function. It's a little harder for me for this tutorial to do that. I think it was better for the tutorial to just leave it right here, so you could be like, oh, for the constructor, this is how you would do this, instead of having to look at another function. But you should do that. That's more efficient if you're going to write actual code. And that's basically what segment trees are. So I'm srcmake. This has been Segment Trees. You can follow me on Twitter and social media and all that good stuff. Make sure you subscribe to this YouTube channel, and thanks for watching. That's been Segment Trees. If you want more videos like data structures, please leave comments saying that, because otherwise I might do something else. I want to do tries in the future, so if you really want tries, leave a comment on that. But if you have some other, data structure that you see in algorithm competitions that don't make sense or you don't see a good tutorial for it, just ask me in the comments and leave a video. Or I don't know. Bye.